So now let us come back to the discussion. We'll start with the H-plane sectoral horn antenna. Now, how we define or how we mention or how we designate different parameters of a sectoral horn antenna. Let us start with that. So this you can see is a cross section of a sectoral H-plane sectoral horn antenna. Since it is H-plane sectoral horn antenna, then A is expanding, not B. B remains constant in the sectoral horn antenna, H-plane sectoral horn antenna. The height remains constant. Expansion is along the width or the breadth. So A is expanding, so we have taken a top view of the antenna. So this gives you a top view, a cross section, which is the top view. In the top view, you can see we have the phase center. From the phase center to the face of the antenna, radius is R0. From the phase center to the face of the antenna at any point, that is equal to R. And then from the phase center to the edge of the antenna, it is LH. Since it is H-plane, so we call it LH. The length is LH. Now, you can see that in this also there is a portion which is up to the face of the antenna, the distance between the face of the antenna to the point from where from where it starts to expand, or from where from the point on the waveguide from where it starts expanding. So that point, the distance between these 2 points is called RH. So this RH is also called L, or the neck of the antenna, the length of the neck. This is called the neck of the antenna. Sorry, this point is called the neck of the antenna. Which point? The point from where it expands, and the point where it has expanded is called the aperture or mouth of the antenna. So from neck to mouth, the length between neck to mouth is called the length of the antenna, L or RH. So we have got these 3 things, these were 4 things: RH or L, R0, R and LH. Now you can find out from this, you can always find out what is the phase difference. Phase difference delta. Delta you can always find out. Delta will be equal to 2 pi by lambda into the path reference. Now path reference on the face of the antenna at any point on the face of the antenna can be found out by considering R minus R0. Now what is R? R you can find out. R is equal to R0 square. R square is equal to R0 square plus X square if we are considering R at a point X from the center, from the center of the face. If it is at a point X, then R0 square plus X square is equal to R square. So from that you can find out delta. Delta is the difference between R minus R0. So find out what is R minus R0. R minus R0 will be R is equal to R0 square plus X square. That, so delta is equal to R0 square plus X square root over of R0 square plus X square minus R0. So it will be minus R0 plus root over of R0 square plus X square. So from that you take R0 square common, root over of R0 square plus X square. From that if you take R0 square common, so that will be R0 into root over of 1 plus X square by R0 square. Now X square by R0 square will be always less than 1, so you can use a binomial expansion. So that will be root over of 1 plus R0 square by X square if you take the binomial expansion. So that will be 1 plus 1 by 2 x square by r0 square. Then you multiply r0 in that, so it will be r0 plus x square by x by r0. So the r0 sorry, x square by r0 square. So r0 square will cancel from r0 square you cancel one r0 with the numerator. So it will be x square by r0 1 by 2 x square by r0, then plus r0. There is a minus r0, they will cancel out. So that will give you approximately equal to this phase path difference is approximately equal to 1 by 2 into x square by r0. So once you know what is the path difference, you can find out what is the phase difference. So at the end, you can find out what is the phase difference, etc. So now using this, you already must have seen these expressions. I am not going to find out what is these expressions. IH square you can find out easily. Alpha H or the psi, alpha H or psi, that you can find out easily using tan, R10 means tan inverse. Then RH, which is the neck of the antenna, RH also you can find out easily. So RH is equal to capital A minus small a into root over of IH by A minus 1 by 4. These are design equations that you have already seen when you have studied our sectoral horn antenna. Now let us come to the other part which is important. Once we know this, then the important part is the two characteristics of a horn antenna, sectoral horn antenna. Let us consider the characteristics, which is the directivity. Let us start with the directivity. So directivity of the aperture D0, this is the expression for the directivity of the aperture that you must have seen. Okay, next. I'm not going to discuss about this. The integral in the denominator that comes out, that is the proportional to the total radiated power. So that will be this is an expression for that. This also you must have seen. And T is equal to 1 by 8 A by lambda square into 1 by R0 lambda 0 in this integral. So this is the expression for directivity. If we use this expression for directivity and plot the directivity, what is important is physically what is happening. So that part is important. So physically what is happening, let us look at this. So now look at this. The maximum phase error actually occurs at the end of the antenna. So end of the aperture at both the end points, the phase error will be maximum. At the center, the phase error is minimum. At both the end points, the phase error is maximum. We have seen, we have just discussed how to find out what is the phase difference or what is the phase error. So that you can write delta max at the end point, delta max maximum phase error can be given in this form 2 pi into T, where T is equal to A1 square or capital A square divided by 8 lambda into rho 2 or capital R0. So T is equal to A1 square by 8 lambda into capital R0 or rho 2. So this gives you the maximum phase error. Then we will come to the far field expression. For the far field expression, EY on the field on the aperture, that will be given as EYX is equal to E0 remains constant. Then pi by AX, that remains as it is. Then for the Z variation, it is of the form exponential minus J beta J into Z, that is capital EY. So that gives you the far field. Based on that is the field distribution. We have a cosine distribution on the aperture. Based on the cosine distribution, this shows you cosine distribution cos pi by AX. So it is a cosine distribution on the aperture. So from that you will find out ultimately the form of the electric field. Okay. Next. Okay. Now let us come back to the directivity. So if you look at the directivity curve, once you know what is the expression for directivity, we can draw the directivity curve. If we draw the directivity curve, you can see a trend in the directivity curve. It goes to a peak, then it comes down, gradually it comes down, then slightly it increases, then it comes down. So this trend continues. Now, when you design an antenna, mostly if you look at the books, in the books it is told or it is written that when you design the antenna, we will design it for the maximum directivity. So look at the one of these curves. I am considering the bottom curve. So let us consider the bottom curve. If you consider the bottom curve, wherever you have got the maximum directivity, that you consider, if you consider that occurs for T optimized is equal to 3/8. When T optimized is equal to 3/8, we get that maximum directivity. Now, if T optimized is equal to 3/8, that corresponds to a phase error, maximum phase error of 135 degrees. So that is when you get this maximum directivity. Now, why it goes up and comes down? The reason you can see it goes up, then it gradually comes down. And you also can see that we can join all the peaks. And if you join all the peaks, they will also be on a straight line. Anyway, I forget that. Now, that is how the book keeps it. Now, in the book, also you can see it goes to the peak. We are asked to design the antenna so that we get the maximum directivity, which is the peak. Now, why before using that way, we must understand what is happening here, why it is going to the peak. Then after the peak, it is coming down, then it goes to peak, then it comes down. Now consider the aperture. On the aperture, the electric field is vertically upward. So electric field will be in this direction. Then as you come to the away from the center of the aperture towards the edge, then the phase differences will creep in. Because phase differences will creep in, so the electric field orientation will, and gradually it will be in vertically upward, then gradually it will be in, you can see the red arrows, that is how the electric field orientation will come. When it is horizontal to the line, this becomes from vertically or upward, it becomes horizontal. So that point is the point where you get the peak. After that, it is turning downward. If you look at the arrow, it is turning downward, which means the contribution due to the vertically upward field will be gradually reduced because of the downward arrow, upward arrow and downward arrow. When you add them, they will be cancelling, exactly not zero, but they will be cancelling. So it will be deducted. So the value will keep on deducting. So directivity ultimately will keep on deducting. Okay. In this figure, actually the x-axis shows you the aperture. So the length of the aperture is shown in the x-axis. In the y-axis is the normalized gain. Now, for the H-plane sectoral horn antenna, B is constant, so it is normalized with respect to B. Since B is constant, so gain by B in dB is given in the y-axis. In the x-axis is your aperture. So aperture in terms of lambda. So this is the x-axis. So as you keep on increasing the x-axis, you can see as you keep on increasing the x-axis, or as you keep in increasing the aperture length. So x-axis shows that as you keep on increasing the aperture length, the phase is changing. The more the aperture length for a fixed length of the waveguide, the more the aperture length, more is the phase error, and we get a maxima. When you get a maxima, from after that it gradually gets decreased. Now, had there been no phase error, actually you would have get a higher undirectivity. You can see a red dashed line from the peak that goes up, where it meets the curve. From that point you would have a horizontal line, so that much of directivity you would have got without the phase error, which means the phase error is affecting the directivity. So we should minimize the phase error. So we should not allow this much of phase error to get a good directivity. We should not allow this much of phase error. I will discuss that in the next slide. This will be more clear. You can say we are getting this much of directivity, high directivity. Why should you reduce the phase error? The aperture will shorten the aperture and get less directivity. So we will sacrifice some amount of directivity. You can sacrifice some amount of directivity for some other reason. Directivity will be slightly sacrificed, but in doing that, the phase error is reduced. If phase error is reduced, then we will get something else, some other thing occurs. So let us look at what happens because of the phase error when you reduce the phase error. Okay. Now, on the relationship between A and R0 for optimal directivity, this relation is, okay, next. A is equal to root over of 3 lambda into R0 or rho 0, whatever you can say. A is equal to root over of 3 lambda into R0, and A by lambda is equal to root over of 3 R0 by lambda. So this is the relationship between the aperture expansion A and R0. So on this relationship gives you the optimal directivity or peak, but we will not use this. You can use slightly less than that, so that the directivity is slightly less. So the error is phase error is less. If phase error is less, then we are going to get some other advantages. Okay, next. And this is a family of, okay, next. Okay, so to understand that, we'll look at the principal patterns. We have seen what is the field. So from the field distribution on the aperture, we have seen the expression. From that expression, you get the expression for principal patterns. As you know, for antenna, the principal patterns are E-plane pattern and H-plane pattern. So the expression for E-plane pattern is this. Expression for H-plane pattern is this. These are available in books. These you must have studied in the horn antenna. So I am not going into this. So what I am going to do is, I am going to look at the pattern itself. So look at this pattern. Now if you look at this pattern, this is very interesting. This pattern is very interesting. Now these patterns are for different T values. Right? If you look at this pattern, the directivity or the efficiency of the antenna is highest, or the gain of the antenna will be highest for the pattern which is at the bottom, because the angular separation, you can see the beam width is smaller. There is a sharp dip, which means well-defined null is there in the bottom part. So that will occur when T is equal to about 1 by 16 or 32, so that way, 64, that value. So T is equal to, T is very small, so that occurs. When T is very small, that indicates a small phase error. So phase error is very small. Almost zero phase error gives you this type of beam. Now, if we go to say a at T, which is equal to 1 by 4. T is equal to 1 by 4 corresponds to delta max is equal to 90 degree. So 90 degree delta max. So look at the third curve. So that gives us T is equal to 1 by 4, or delta max is equal to 90 degree. So if you get delta max is equal to 90 degree, you can see that beam width is broadened. It is coming down, then there is a good shoulder, a drooping shoulder in the pattern. So that means the energy is radiated in the undesired direction, not in the desired direction. There is in the desired direction less amount of energy, and some amount of energy, substantial amount of energy is radiated in the undesired direction. Look at T is equal to 1 by 8, which is delta max is equal to 45 degree. So there also you can see there is a shoulder, but that is sufficiently below the T is equal to 1 by 4. So delta max is equal to 45 degree is equal to this. Now if you go to T is equal to less than 1 by 4, then you are going to lose more energy in the undesired direction. As you can see, as you go to the upper curves, those curves, there is no null, nulls are not properly visible. The energy is in the undesired direction. Energy goes in the desired direction, the energy amount gradually reduces, because more than 10%, 20% energy is in the undesired direction. Therefore, we have to keep the phase difference or the phase error minimum. So the phase error will be between 45 degree to 90 degree. Phase error is a good value. There you can see that it is about minus 20 dB can be lost, but if you more than that, you lose less than minus 10 dB, 0 to 10 dB. So those portions will not be acceptable. So when you design an antenna, you use it for minus 20 dB, between minus 20 dB, minus 10 dB to 20 dB, that will be acceptable. So this is another pattern. So principal pattern, you can see the expression for H-plane sectoral horn antenna. This shows the principal pattern. Here also you can see the H-plane is the solid line, E-plane is the dashed line. So E-plane is almost a omni antenna, omni pattern, but H-plane, you can see what happens to the H-plane. The H-plane pattern we get an approximation. This expression is an approximation for H-plane pattern. This is the consequence of phase approximations made in R. Based on that, this approximation is given. And accurate values for this F, this can be found in the books. So don't worry about that. Look at the books, or you must have studied that. So this is about the H-plane sectoral plane. Now if you come to the H-plane pattern, you can see the H-plane pattern is not very directive. It is quite broad. This also is quite broad. The beam width is quite broad. In this case, from minus 30 to 30 is quite broad. 60 degree beam width, more than 60 degree beam width. So it is quite broad. We do not require this. Okay. Next. Now come to the E-plane sectoral horn antenna. The expression for directivity you must have seen, so I am not going into that. Again, here you can see the directivity as in the case of the H-plane sectoral horn antenna. You can see the curve for directivity in the E-plane sectoral horn antenna. Here also you can see delta max, maximum phase difference, is equal to 2 pi s, where s is equal to b1 square by 8 lambda rho 1, Rho 1 also you can write as rho 0 R0. B1 square B1 you can write as capital B. So S is equal to capital B by 8 lambda R0. Capital B square by 8 lambda R0. In that form you can write it. The optimized value of S in the books you will get, it is equal to S optimized is equal to 1 by 4. So once you put S optimized value 1 by 4, then delta max will be 2 pi into S or 2 pi into 1 by 4, which is equal to pi by 2 or 90 degree. So S optimized is equal to 90 degree. When S optimized is equal to 90 degree, so corresponding to that B1, S is equal to B1 by 8 lambda rho 1, B1 square by 8 lambda rho 1. So if you draw B1 along the x-axis and the directivity along the y-axis, the B1 that corresponds to this S value, this value for which delta max is equal to 90 degree, when delta max is equal to 90 degree, for that B1 you will get the maximum gain. So maximum gain occurs, the peak, look at the lower figure, the peak occurs at this point. Okay. So on the optimal relationship between the flared height B and the horn apex length R0, on that produce the maximum possible directivity is B is equal to root over of 2 lambda into R0. 3 lambda is for A. So B is equal to 2 lambda into R0. If you take R0 common, then it will be 2 lambda by R0. So that way it will be there. Okay. So now we see a family of curves, lambda d e by alpha is in the x-axis and versus b by lambda, which is in the y-axis. With R0 being the parameter, we consider if you keep on changing R0 or rho 1, what will be the value of these antennas. So rho 1 is equal to 100 lambda, means R0 is equal to 100 lambda. 100 lambda means it is very large antenna. If you consider 100 lambda, let us consider 100 lambda. Let us consider lambda to be 30 centimeter. Or if I consider 3 gigahertz, antenna of 3 gigahertz, 3 gigahertz means 3 into 10 to the power 8 meter, or 3 into 10 to the power 10 centimeter divided by 3 into 10 to the power 8 meter divided by 3 gigahertz means 3 into 10 to the power 9. So 3 cancels out, 10 to the power 8 by 10 to the power 9, which means 10 to the power minus 1 meter. 10 to the power minus 1 meter is that into 100. So that is 10 centimeter. So 10 centimeter into 100 lambda. Rho 1 is equal to 100 lambda. 100 lambda into 10 centimeter is 1000 lambda. So rho is equal to 1000 centimeter. 1000 centimeter is 10 meter. So it is quite a large antenna. So same when you come to about 6 lambda or 10 lambda, it will be 10 times less than that. If we come to 10 lambda, it will be 10 times less than that. So from that, it will be half of this 10 lambda will be about 6 lambda. So it is a small antenna. So how we usually require a smaller horn antenna for feed. We don't require a larger antenna which will block the parabolic antenna, or the feeding antenna should not block the aperture of the reflector. So you require a small antenna, so consider a small antenna. Of course, the aperture size is small. Since aperture size is small, gain will be small, because 2 pi a square by lambda gain. So based on that, the gain will be small compared to the large aperture. But here also, the explanation that we discussed for the H antenna holds. If I have larger phase error, will have less gain compared to lesser phase error. That is one point. Then other point is we'll consider the pattern. If we consider the principal plane pattern, then we'll see what is happening in this case also. As in the previous case, we can sacrifice some gain, but with less this one phase error. So we go for less phase error, so efficiency will increase. As in the previous case, here also efficiency will increase. Next. Now, unnormalized patterns are these are the expression for normalized patterns, normalized D-plane pattern and normalized H-plane pattern, and these are the expressions. I am not worried about the expressions. You know the expressions. Then look at the principal patterns, calculate these principal patterns. These also are available in book, so I am not worried about this. I am worried about this and the E-plane pattern. So look at the E-plane pattern. If I look at the E-plane pattern, delta max is equal to 90 degree. You can see it is at around 13 dB, 10 dB, more than around 10 dB or minus 10 dB or minus 13 dB. There is a good shoulder there at delta max is equal to 90 degree. If I go for a phase error of 90 degree, it is at minus 13 or minus 14 or 13.4 somewhere there. So if I look at there, that is more than 10% of the power is radiated in the undesired direction. Power is radiated, but in the undesired direction we are radiating more than 10% of the power. Same thing, if I reduce the phase error to 45 degree, it comes down to about 17-18 degrees, 18 dB. So that is quite good. If it comes down to 17-18 dB, that is quite good. So delta max, we cannot go to delta 0. That aperture will be very small, gain will not be there. So to have some gain, we have sufficient amount of gain, and most of the energy is radiated in the desired direction. For that, you can go to delta max is equal to 45 degrees. So that is the allowed phase error that we can see. The same thing we can see in the polar plot. If you look at the polar plot, you can see the shoulder. Shoulder is around 10 dB. There is shoulder on both the sides, and the null is not well defined because there is a shoulder. You don't have a well defined null. So we require actually a lesser phase error for a better principal pattern radiation. Now I will come to the pyramidal horn we have seen. So I am not going into to discuss this. Next. For the pyramidal horn, aperture field is this. The patterns will be available to you in the book. Skip this. And directivity is this. This gives us a animation of the horn antenna. You can see this is an ideal horn antenna. Now you can also see that as the field leaves the horn antenna, inside the waveguide it is a plane wave. As it comes to the horn antenna, gradually it becomes a spherical wave. So as it leaves the horn antenna, the spherical wavefronts are clearly visible. As you go away from this, these spherical wavefronts gradually will expand. So they will become gradually, you can see the top form. Top is gradually becoming a straight line or a plane wave. So at a sufficient distance, it will become a plane wave. This is this in the far field, you will get a plane wave from this antenna. And the power, you can see how the power is distributed along the center. Maximum power, this is typical. As you go away, the power will reduce. This is the radiation pattern, 3D pattern. Now let us come to the design of the antenna. You can look to this book, Handbook of Antennas. by J.D. Krause. So if you look at that book, in that book for the horn antenna, a design curve is given. So when you are given a horn antenna design of a horn antenna, always is done with respect to a standard gain horn antenna. So gain is to be standardized for the horn antenna. So to design the horn antenna, first gain will be specified. Then what is specified is what is the beam width in both the planes, both the principal planes, what will be the beam width. So from this knowledge, you have to find out what will be the aperture length, what will be the length of the antenna or L. So L you should know, aperture length, which is capital A, capital B, or here it is shown AE lambda. AE lambda is the expansion in the E direction for the E field, the expansion in the E direction similarly, which is actually capital A. H lambda is actually capital B. So those are the curves. Now once the gain is specified, here it shows a gain of 19 dBi. Once the gain is specified, draw a vertical line from the gain axis that will meet these three lines, L line, A line, and B line, capital B line, or AH line and capital A and AE line. So where it meets those lines, draw a horizontal line, so that will give you the lengths. So AE, where it meets AE, draw a vertical line, whatever length you get, that is the AE length. Where it meets L, draw a vertical or horizontal line, wherever it meets the y-axis, that is the length of the antenna. Then wherever it meets AH, draw a horizontal line, that is the AH antenna. So once the gain is specified, it is quite easy to design the antenna, actually quite easy to design the antenna aperture and length, those things you can design. Then once you have designed the antenna, then you have to feed the antenna. Now let us come to the feed of the antenna, how you are going to feed the antenna. So before that, maybe I will take a break of 5 minutes, then I will come back and we will start. We will stop after the feeding, then we will discuss other things. So let us take a break here, 5 minutes.